Right, here we have a little bit of a more sophisticated, I use that word loosely, circuit to drive this motor, which if I just lift it up you'll see that it's just something I had running around in my cupboard. It's actually not the best motor to demo this with because this has got a very high magnetic, you can feel it as I turn it, it doesn't want to go round and then it springs round, so it's going to have a lot of resistance against any kind of current going in there. What I'll do, I'll dig out a proper computer fan from a computer case over the next day or so and plug that in. You'll see how much easier it spins. So we might have a little bit of problem with this motor, but it will give you certainly a flavour. There's a couple of other things about this project. You may notice, if you've been watching my other videos, which doubtless you have by now, we're using the shield that plugs in on top of the Arduino Uno. So that's this thing on top. It plugs directly in here and extends all the pins back out, as well as giving you this tiny little breadboard, which you can put a simple circuit on, as in fact we have done. Little simple circuit, which I'll draw out in a minute. Because this motor, once again, is not particularly suitable for this project because this doesn't need 5 volts, this needs 12 volts. It will just about run at 5, but unfortunately it then requires more current than what the Arduino pin can give out. The maximum for Arduino pin is, I believe, 40 milliamps, and this requires 60. So that would probably burn my Arduino out or some such thing, and I don't want anything like that to happen. So we're having to run this on 12 volts, which would be fairly standard for most motors, I think. You wouldn't run them directly from an Arduino. So we're running this from 12 volts, but that requires a certain added complexity in the circuit here, but it's hardly complex. I use that word also with literary license. So this is running off 12 volts, although the actual Arduino, of course, is running off 5 volts with this little plug here. So we're using a transistor to switch this motor on and off, controlled by the Arduino. So let's just draw a little circuit diagram out, just so that you get the idea of what it is I'm doing here. Right, a simple little circuit diagram then. We have the output from pin 11 from the Arduino. So that's the pulse width modulated output. Now that's going now into a standard NPN transistor. To be quite honest, I should really have put a little resistor at least in here, but I haven't, because it just doesn't seem to make a lot of difference, and I want to make sure that this transistor is turned fully on with each pulse, not partly on, otherwise that generates an awful lot of heat here. We wouldn't want that. So that goes down to earth, which is sort of a common earth from both the old, for the Arduino, and our 12 volt supply. So our 12 volt supply is going to come into the motor here and the transistor, and I suppose that's about as simple as you can get it. Now what I've also done is left the LED in and the resistor, so also from here in fact that's the wrong way around, it's going that way with a 220 ohm resistor to protect it. And now one thing you must be aware of, that this motor, as it revolves, does give off a fair bit of back EMF. Which means you get spikes on this supply line. So our 12 volt supply line here, that gives off a lot of spikes that could damage either this transistor or indeed the Arduino. So to prevent that, we put in a diode, protection diode, like that across the motor, so that any back EMF is blocked. Also, you could put a 100 nanofarad capacitor there to stop any noise. Now that I know, you see, that is already on this motor, so I didn't bother. But certainly the protection diode, which would be a 1N4001, in fact any of those silicon diodes would do just for now, 100 nano just for the capacitor and your motor, and this is Now this is actually a ZTX 300, but don't go out and rush out and use those. Any standard NPN type transistor would do. Let me see if I've got the specs for that one there. I mean, it's a fairly simple one. Camera at the screen again. So there we are, ZTX 300, NPN, small signal transistor, silicon, blah blah blah. And the specs are, well, 25 volts, sort of maximum voltage, 5 volt emitter base, when we're not going to exceed any of that. 500 milliamps, well our motor only takes 60. I have to watch the power though. The power is 300 milliwatts. So if we're taking 12 volts at 60 milliamps, we just squeak in there, don't we really? Remember that, back to the drawing board, remember the way to calculate a lot of these things. V, I, R, do a little triangle and a block, so that's I, that's R. So voltage is current times resistance, or voltage divided by resistance is current, voltage divided by current equals resistance, and power, which is in watts normally, is voltage times current. So we've got 12 times about 0.6. So that's about 720 milliwatts, which, well, according to that spec sheet, we are exceeding, because it says 300, which is a bit lower than I expected. But because we're only switching it on for so very short periods, I'm not expecting any problems in this case. But if yours goes poof with a little bit of smoke, don't blame me. Just kidding. We'll be fine. We'll be absolutely fine. So that's the circuit diagram. And I suspect this will be fairly common, because you're not going to drive any kind of motor directly from an Arduino. Well, not that I can think of. I mean, if it's on a robotic arm or something, certainly not a wheel, a motor that's wheel. You need too much current for that. You need lots of torque. So that's sort of a basic circuit. It will do for what we want to do for our demo. Now, of course, pulse width modulation is all about torque, as in T-O-R-Q-U-E, because when I showed you that original diagram, if I can just dig it out again. So this original diagram, we'll be talking about, let's look at this one, 25% mark space ratio. When it's actually on, and even though this might be just for a tiny fraction of a second, but many times a second, you're going to get the total 100% torque out of this, more or less. It's slightly more complicated because it takes time for current to flow through a motor due to its magnetic properties, so it doesn't actually switch straight on inside the motor. But from a theoretical point of view, you have got maximum torque for that period, and then nothing, and then maximum torque again, which is funny enough how electric cars work. You need to give them this pulse width modulated current supply in order to get them to drive. You couldn't reduce the voltage and hope anything can happen. They'd stall. So, okay, that's what it's all about. So let's turn this on, which is already set up, and see how it looks. Right, let's plug this in. There it goes, ta-ding. And what's happening? Oh, I can hear a noise. It's trying to move, and we're off. The LED's quite bright, it's going back down now. Oh, and what did I say about stalling? This has stopped. It's trying to move, you can see it's trying to. This is why it's such a bad motor for this demo, because it's got too much resistance in it. If I set it off, a bit like starting a propeller on a World War I plane, off it goes. But once it's stopped, it's stalled now. It needs quite a bit of power to get that going again. But you can see the LED is sort of reflecting pretty much, so it's going down to nothing. Well, that stops long before that goes down to nothing. So it just goes to show we're going to have to adjust our parameters a little bit to get this to work properly. Right, let's do that now. Right, just uploading a new program now with some different parameters in for this motor. Let's see what that does. Still not very good, is it? It's hardly what we'd call smooth, but you can see that it does speed up and slow down. Basically what I'm doing is reducing the minimum amount, the minimum pulse that we're sending out that could possibly be of use to that motor. The problem is once it's stopped, it takes a lot to get it going again. As I say, I can spin it, look. Once it's, now it slowly spins up. There's too much resistance on this. Right, I'm going to get the extractor fan, the computer case extractor fan, connected up to this over the next day or so, and we'll come back and I think we'll see a much different behaviour compared to this. Very similar to the behaviour that I experience now in my computer cupboard with those extractor fans that I showed. Much, much smoother. Right, until then. So here we are then, a couple of days later. I've dug out this extractor fan from the loft where I have all my spare parts. This was an extractor fan from a computer case from about a decade ago when such things were prevalent. Now this is a much easier model to work with, and also just to make it even easier for us to see what's going on, I've changed the circuit here. Rather than having that ramping up, ramping down loop, which was all a bit quick, I've changed it now for potentiometer control, so we can turn this little pot here as a sort of a speed control. I'll post this circuit and the code that goes with it all on the end of this video, so grab your code down there. But what we can do is, first of all, let's see how it all works, and then we'll go through the code very quickly because there's some interesting little bit that I found about this as well. So the code's been uploaded, the power has been connected as per previously, 12 volts, the fan's in exactly the same position, and the potentiometer's at 0. So if I turn this up slowly, you should see, hopefully, the fan there starting to want to move, and it's off. And as you can see, the LED, although you see it as white, I see it as a very lovely red, is also glowing. And if I turn it down and down and down, obviously the fan has a certain amount of inertia, which means it keeps it going even though there's not enough power. Now you can see how slowly that is going around now compared to what was happening before. I can probably get it just a tad slow before it stalls on me. That's going pretty well. Now I'm going to disconnect the camera from its mounting here and hold it really, really close to that fan to see if you can hear what I can hear. Right. So let me just get this camera in the right place and see if we can hear something. Well, I hope that picked it up. I'll certainly try and boost the sound a bit when I put this onto the editing suite. But frankly, there's a really annoying sort of humming whine coming from that motor. And I remember something like this happening when I first made the circuit for the computer chip, sorry, the microchip version in my cupboard. And I wondered what it was all about. And the reason is because the pulsing of this motor, the Mark square wave, is being output by default from the Arduino library as within the audible range. The default for pulse width modulation is 490 Hertz, which is like a low droning whistly sound, which I'm hoping, as I say, you picked up from there. So if we go to the computer screen at the moment and zoom in on that, there's this little table I want to get told. Right, now it's a little bit grey because it's actually commented out, but we can see there that by default the divisor from the base frequency is 64, which means the output from the pulse width is 490 Hertz. And frankly, I've never known anything so silly, because I can hear that motor even now as I'm recording to this. There's this annoying whine, and I know this is the quiet office that I'm recording this video in, but believe me, it's extremely irritating. Now, luckily, there's this little line here, a little bit of magic we can do to set the timer output frequency to something different. Unfortunately, it's a fixed value. The next one up would be 980 Hertz, which is probably even worse from an audible point of view. It's just a shade under the 1 kilohertz, where our ears are most sensitive. Then just a shade under 4 kilohertz, and then finally, oh thank goodness, 31 kilohertz, which is well outside anybody's hearing range. I mean, even a dog might not hear that. So what I'm going to do is change the code now. Zoom back out on here. Right, so I'm going to change the code while it's running to have a different output frequency, basically 31,000 hertz, 31k. So let me just do that even as we do it in real time. I can always edit out the gaps, don't worry. Right, now we should see the light go off. There it is, as the program's being uploaded. Fan stops. Right, the light's back on, but you notice the fan hasn't come back on yet because we've reached the stall current. If I were to spin it manually, it might pick up. Let's have a look. No, it's slowing down, it's slowing down. Well, actually it's sort of just about limping along there, isn't it? So let's just up it a little tad. There we are. Now, the beauty of that is it's now silent, and I do mean silent. The fan itself, of course, being from a computer case extractor, is pretty much silent anyway. The only noise you get from one of these is the soft hush of air coming out, and I can't hear anything at the moment. And now, because the pulses to here are well outside the audio range, I can't hear that either. It's a huge relief. Now, of course, if you're building robot arms or cars or something, that 490 hertz pulsing will make absolutely no difference to you whatsoever. It's not going to be a quiet environment. And there is a downside to having the frequency so high. The range of control for a motor like that reduces as the frequency goes up, because those very high frequency pulses, and let's face it, we're doing 31,000 of them every second, doesn't give quite enough oomph to that motor to get it past the inertia of the motor, because this motor is effectively an inductor. It's a big coil, isn't it, of wire, so it will resist current flow. So in that 1/32 of a second, the amount of current running through here is probably tiny. So we have to increase the mark space ratio just a tad to bring it up to probably, I don't know, 20%. We'll have a look on the oscilloscope in a minute, the recordings I took. So you lose a certain amount of control. If you want that ultra fine control, you might have to go back to round about the default, the 490 hertz. But then you do get that noise problem if you're in a quiet environment. So the question is, where did I pick this information up from? Well, it was actually on the Arduino forum itself, or the Arduino website. Anyway, let's move this across here. Now, here it says about adjusting the Pnw frequencies, and this article, I don't know who I can attribute it to, really. Well, it's thanks to Valiero Spirati for something, for the original one, I guess, and Maestiar. Anyway, there's obviously quite a few clever people here who've figured out that by adjusting the divisor in this manner and the timer, you can change all sorts of values on here. And this is really more detailed than I want to go into. Just bear in mind there is a warning here about the Arduino Mega. It's slightly different because it has different timers. But all this is a bit too much for what we want to do here. I'm using pin 11, that's this one here, because that's using timer 2, and this is the little table that I copied into that bit of code. And that's what matters. Now if you're using a different pin, you'll have to use a different timer. So if you want to use 9 and 10, you use timer 1, and to say 5 and 6, which is shared by timer 0, and that's the millis in delay, you really want to avoid that if you can. But here are all the settings anyway that you need. So it's these lines underneath all these that do the magic. And to be quite honest, I don't want to get into how and why and all the rest of it, just that we can. I think it's amazing that we can do this. Right. Okay, that's enough on that score. Let's have a look at what I found on the oscilloscope to show that the mark space ratios are very clearly being output there. Now it's on the 30, the fixed 30 we said right at the end, just to prove that the motor will keep going round. Now it's back, ramping up again, almost up to the 100%. It did seem to touch there just for a bit, didn't it? It was 100%. Now it's going back down again, and there it is, ramping up quite quickly. In fact, it ramps up, doesn't it? Maybe we can slow that down the code a bit. But there we are. That's a pretty standard look at how it might be for a typical pulse width modulation. Okay, moving on. Well, I think that sort of covers it really for pulse width modulation introductory course. I'll post the code for this, and this analog pot that we're using here to control the speed. I think I might do a little video about analog inputs, whether it's a simple thing like this pot here, or a rangefinder, ultrasonic rangefinder, that'll use analog as well, just to tidy all that up. In summary, what this Arduino is doing is checking the value on an analog input pin to say, out of 0 to 1023, what's the value on here? And then we're dividing by 4 to put the output pulse from 0 to 255 on the output. So it's dividing by 4 effectively. I'm reading the voltage, 0 means 0, 5 volts means 255, and anything in between, divide by 4. It's a fairly simple piece of code. There we are, that is all the code there is. So we basically read the analog pot on analog 0, the pin. There's a debugging statement to print it out just to make sure it works. Then we divide by 4 and put it out via an analog write on the LED pin, which is pin 11. That's all there is to it. And that's how you can make a variable speed fan for a computer cupboard. And of course you can automate the bit that's currently being done by the pot with a temperature sensor, which is also analog input. So yes, definitely a video on analog inputs coming up in the near future. Okay, that's it. Thanks for watching. I hope you're finding these videos useful and interesting. Remember, you can leave comments down below, and also click that little button that says subscribe. Okay, thanks for watching, and see you in the next video.